The GS20 drives have lots of PID options and features. But that also means there's lots of additional parameters to wrap your head around, and that can make getting started with PID even more intimidating than usual. So in this video series, we're going to show you how to filter out all the chaff and get a simple PID application up and running quickly. Our goal is to have the GS20 drive use PID to automatically maintain the pressure in this system regardless of how many valves are open. This GS20 drive is controlling this motor, which is pumping water to these manual butterfly valves. The tank drains to a reservoir, which feeds the pump through this check valve. This 15 psi pressure sensor sends a 0 to 10 volt signal back to the drive so PID can monitor the system pressure and adjust the motor speed accordingly. I'm assuming you're familiar with the PID feedback process where you tell the drive you want it to be at some value we call the set point. It monitors the system pressure via the process variable, takes the difference between the two, and uses that error signal to figure out how to adjust the control output. We can also bypass the PID calculations and manually drive the output, which helps us test the system. This system is set up like this. We'll enter the set point via the keypad, and the 0 to 10 volt process variable will come in on analog input 1. We'll set up the drive's local mode configuration to be just a manually controlled drive where we use the keypad's potentiometer to directly control the drive's output frequency and the keypad run stop to start and stop the motor. We'll use the remote mode configuration to run PID, and we'll use some external switches to control the run stop, and if PID is automatically controlling the output, or if we are manually controlling the output. And we'll need an external switch to switch between local and remote modes. Sounds like a lot, doesn't it? Yeah, it is, but I have this cheat sheet that makes it super simple. These are all of the things we need to configure to make this happen: the set point, the PID algorithm, the control output, and the process variable. And of course, we need to configure the motor and the drive. The good news is, everything in blue is a default value. So all we have to do is enter the values for the yellow squares, and we're done. Let's walk through it. For the set point, we just need to tell PID where to get it from. I have little notes in each of these squares to remind me what all of the relevant options are. We want to enter the set point from the usual local or remote setup, which we'll configure down here in a minute, and that's the default, so we don't need to do anything here. For the PID portion, we're just going to start with the blue default values and tweak them later. In general, you'll find these default values will be a great starting place for most industrial applications. Notice that the GS20 gives you a choice of two different PID algorithms. In the dependent PID algorithm, changing P changes I and D. That simulates the old analog systems where when you change the gain of the system, you change everything else too. In the independent PID algorithm, P, I, and D can be tuned independently without affecting each other. That makes it easier to tune because messing with one coefficient doesn't change the other two. This is what you'll find in most modern digital systems. We're going to use the default, which is the dependent PID algorithm. There's lots of options for manipulating the control output. I'm just showing two of them here. By the way, you can see all of the PID options we're not using down here. Here are the other options for the control output, for example. Okay, we need to tell the drive that the process variable is coming in on an analog input and configure analog input 1 to do that. I'm also going to add a small amount of filtering on that analog input. You'll really want to keep filtering as small as possible. A large filter value will slow down the response of the PID algorithm. Let's tell the user display to show us the process variable. And of course, we need to tell the drive what motor we're using. Finally, we need to configure the drive. We'll be using the remote configuration for PID, and we want the frequency source, which will be our set point, to come from the keypad, and run stop to come from the digital input. Now, I don't want to use the potentiometer for my set point because someone might bump it and mess it up. This just says local mode runs local parameters, remote mode uses remote parameters. In local mode, we will use the keypad's potentiometer to control the frequency because it's easy. And we'll control the drive via the keypad's run stop button just to show you we don't have to use the external switch. We'll leave the max frequency at the default 60 Hz, but I'm going to change the min frequency to 0 to make our math easier. You'll see why in part 2. You want to keep the acceleration and deceleration as short as possible and let PID control how fast the drive ramps up. Now, if you get overcurrent faults, You can increase these to slow PID down if you need to. Finally, we want digital inputs 1 and 2 to control run stop and forward and reverse. We're not actually using forward and reverse in this demo, so I don't even have it wired up. It just comes along for the ride when you choose this option. Digital input 3 will be our local remote selector, and input 4 will select if PID automatically controls the motor or if we manually control the motor frequency. Well, that's it. Over here you'll find a list of all the relevant PID parameters in numerical order. That makes them a lot easier to enter into the drive. And look, we didn't change any of the blue default values for the PID parameters, did we? All we did was configure the motor, the drive, and the I/O. Not bad at all. You can download a copy of this tool at the link in the description below the video. I went ahead and entered all those parameters, wired everything up, and got the pump primed. We'll be using the free GSoft2 scope function to monitor the system, and I added a digital panel meter to monitor the output of the sensor because it automatically converts that 0 to 10 volt signal to PSI for me. So we said in local mode, we want to be able to control the run stop from the keypad. Yeah, that works. I see the water squirting out of that open nozzle. And we wanted to control the frequency from the potentiometer. Yep, that works too. So how much frequency do I need to get my system to 6 PSI? Let's tell GSoft2 to show us the drive frequency and the analog input. If I play with the potentiometer a bit, it looks like around 40 Hz with one valve open will get us close to 6 PSI. On the scope, we see the frequency in Hertz and the analog input in percent. Okay, if I open a valve, we see the pressure drop. So I'll increase the frequency to get the pressure back to 6 PSI. Open another valve, pressure drops again. And I'll raise the frequency again to get back to 6 PSI. Open the last valve, pressure drops, so I raise the frequency to compensate. And if I close the last 3 valves, the system pressure goes way up, so I reduce the frequency to get the system pressure back to 6 PSI. So the good news is, our system is capable of keeping the system at 6 PSI regardless of how many valves are open. Now that's important. If you can't make the system do it manually, well, PID won't be able to do it either. Now we just need PID to automatically change the motor speed when the pressure changes. Join me in part 2, where we'll flip over to remote mode to turn PID on, and we'll play with it for a while to get comfortable with how PID works in the GS20 drive. Click here to see all of the GS20 variable frequency drive video tutorials. Click here to subscribe to our YouTube channel so you'll be notified when we publish new videos like this, and click here to learn about all of Automation Direct's free award-winning support options.